So, Chapter 8 is the Electrons in Atoms chapter. And what we're trying to do in Chapter 8 is come up with a good understanding of how electrons actually behave in atoms. Um, what are actually electrons is one of the basic questions we're going to ask. And then this applies as we move forward into not only a lot of the properties we see of atoms on the periodic table, but we also will be heading towards how do compounds and molecules form. So how does O2 form O2, and what is the structure of the electrons in a molecule like O2? Those are some of the questions we're heading towards answering. So what I've done in this chapter is, because we have to sort of go over a lot of physics in terms of wave properties and particle properties, what I've done is sort of laid out some of the key skills that you need to have in this chapter to sort of understand what's going on. And I'm not going to go over this slide right now, but as we go through the slides and we finish sections, I'll talk about some of these equations, and they should be familiar to you by then. Well, where does this all begin, right? People have been arguing about the structure of atoms for a long time, and it actually begins with the study of light. And Isaac Newton and a guy named Huygens, which is apparently not how it's actually pronounced, but apparently we can't pronounce it very well. You could Google that and you'll see. But Newton and Huygens argued on different ends that light was made of small particles, and that was Newton's contention. And Huygens was saying that light was composed of waves. Now, there was no, I mean, when you think about what a wave is, like if you're in the ocean, you know that water waves, right? There's waves made in the water. And in sound, what waves, right? Well, it's the air creates types of waves which are known as compression waves. And like a slinky, you can see waves in a slinky or string. And in all those cases, we kind of know what's waving. In the water, in the ocean, it's the water, right? In air, it's the air. In a string, it's the string. You can see it's a tangible thing that's waving. And the waves contain a lot of information about the wave, the length of the wave, and the frequency at which the waves go past a point tells us a lot about their energy, for example. But part of the argument between Newton and Huygens was what's waving if it's a wave. And so now we get to that was 1700s, this is 1800s now. We're talking about Michael Faraday. And what Michael Faraday did was he created an iron ring, and he wrapped it in wire. You can see the wrappings, right? And so inside there, there's electrical wire, copper wire probably. I don't know if it's actually copper, but it's probably copper wire. And there's a little gap here. And one of the properties of an electric current, like when you run electricity through this wire and it goes around and around and around and around and around like this, is it will induce a magnetic field at this gap. And what Faraday did was he took a prism that he had made and he shined light through it, and he was able to get the light to turn, that is, change direction, right, by passing a current through these wires. And I know this sounds like, oh, I could do this if I went to Radio Shack kind of thing, and you probably could do it by going to Radio Shack, but you have to remember Michael Faraday did this when there wasn't a Radio Shack. So he actually, every single component you see here took him time to build, years to build some of it, but took him time to build. He had to make the wires and the insulation, and he had to make the iron ring that's here, and the piece of glass that he used, he actually even made the piece of glass. So that was one of the things that took him the longest time, is perfecting sort of the recipe for that glass so it would have the properties he needed for the experiment. So anyways, one of the things that Faraday said is that I have at last succeeded in a bunch of other words, magnetizing a ray of light. And one of the principles that came out of this was that there must be an electromagnetic field, because the electric part, right? And then there must be a magnetic part, because it was able to interact with the light So light has both electric and magnetic components to it, and this became known as something that we call now the electromagnetic field. And it's around you all the time, and that's the medium. It's not matter, but it's the medium in which light travels, and travels as we kind of know it now as a wave and a particle both. Okay, so both Huygens and Newton ended up being right, even though they argued for years about it. For many years, Newton won just because Newton was more famous, basically. This is just a background picture, but when we talk about light waves, we think of things that are continuous. And this is a picture of Isaac Newton. This is a picture I picked up in Cambridge. I took it in a display along with this, and this was actually Isaac Newton's prism that he was using to sort of wow the ladies, I guess, in his laboratory. I don't know, it seems really weird. But anyways, when we think about a light wave, we think about a couple of different things. We think about its wavelength, okay, and we think about its frequency. I think I better I was using black and you can't see it. Wavelength. We think about its frequency. So let's define those different things. So we think of waves as being continuous, and they're oscillations of increasing and decreasing magnitude. We think about them oscillating around like a zero value here, right? And then it's an increase in either the electric or magnetic component, and then the decrease in the same. The amplitude of the wave is from 0 to the peak, but could also be considered, this is also considered to be part of the amplitude as well. It's just in the opposite direction, right? So it should be the same height. And the wavelength is the peak to peak distance. Now, all it has to be a wavelength, which is lambda, so we just go like this, right? Lambda is the wavelength. It just has to be any 2 points on the wave that are the same. So this could define the wavelength as well. Okay, so this is the same, that's the same length from here, let's say, to there. Now, one of the general principles of waves is if you take the frequency, okay, and I'll talk about what frequency is in a little bit, and the wavelength, and you multiply them together, you get the speed at which the wave is traveling. Okay, so nu, frequency, has units of per second. Let's do it like this. 1 over s. And also is abbreviated as hertz. A hertz, like it's named after a German scientist, but like that, hertz, right? Abbreviated HC is per second. So, you know, if you're standing, this is you at a beach, and you're standing in the water, it's the waves that pass a point per second. So if you're standing in the wave and you count, right, you might get only, because usually the waves aren't going that fast, but you might count like 1, 2, 3, 4, 1, 2, 3, 4, and then every 4 seconds a wave passes you, then the frequency would be 0.25 hertz. That is, there's a quarter of a wave per second if it takes 4 seconds for the waves to go past you each. Okay, so it's literally waves per second. And then lambda is the wavelength. That's usually in meters. So for any wave, if you multiply, frequency and wavelength, right, you're going to get per second, and you'll get meters like this. So that ends up being meters per second, and that's the velocity of the wave. Now, most waves can travel at different speeds depending on the density of the medium that they're traveling in. As it turns out, light waves can travel in the absence of like a physical medium. And light generally in a vacuum travels at the same velocity regardless of the point at which you're observing it. So like if you're in space, right, or if you're on Earth, or if you're in the ocean, so regardless of the density of the material around you, water travels roughly at 3 times 10 to the 8th meters per second. So this gives sort of an interesting property for light waves, since they're both like lambda nu times lambda are equal to a constant that's 3 times 10 to the 8 meters per second. For light waves, when this goes up, right, this goes down. They're inversely related to each other. So if you shorten the wavelength, that is, the wavelength lambda gets shorter, the frequency has to be higher. So they're inversely related for light. So another aspect of waves that we discuss is their amplitude, okay? And we'll see why amplitude is a little bit trickier later. But the amplitude of a wave indicates how bright it is, okay? So this is something that many students have to sort of dissociate. Two things. Wavelength, right, which is related to color, and amplitude, which is related to brightness. The bigger the amplitude, as is shown over here, the brighter the light will be, okay? And the smaller the amplitude, the dimmer it will appear to be. And then wavelength and color are related in such a way that if you look at Roy G. Biv, if you guys are familiar with this, this is red, orange, yellow, green. This is blue. The weird one is indigo and violet. Okay, so Roy G. Biv, though that's the order of the colors in a rainbow. So when you're looking at a rainbow, there's always a red side and a bluish violet side. My eyes, I think I'm just not very good at distinguishing all these. I definitely know blue, but indigo and violet just start to look all the same to me. But the colors of the rainbow go in this order. Longer wavelength light, okay, red is a long wavelength light. Blue is a shorter wavelength light. And so it turns out this is long wavelength, sorry, and this is short. And what that actually means is, right, short wavelengths, right, mean high frequency. And then long wavelengths means low frequency. And what we'll find out as we go through this chapter, frequency is directly related to the energy of the light. And we're going to call something called photon energy, and we won't get to this for a little bit, is proportional to frequency. So if the frequency goes up, the light energy amplitude, sorry, not the amplitude, but the light energy goes up, okay? The light energy for a photon, and I'll explain that in a little bit. So let's do which is the best, right? Which statement best describes the difference between a bright green laser and a dim red laser? And take a second to look at these statements. And you might want to pause, and then I'll go through and explain each statement. Okay, so I wrote Roy G. Biv up here, right? And red versus green, I know that they're going to have different wavelengths, and because they have different wavelengths, right, because here's red and here's green, they're going to have different frequencies. So I'm going to keep both those things in mind as I read through these statements, okay? The other thing that I know is a bright green laser has a larger amplitude. And a dim red laser is lower amplitude. Okay, so let's read through. It says two lasers emit light of the same frequency, which we know is not true. The light from the green laser has greater amplitude. So the second half of this statement is true, but the first half is false, so we can ignore that statement. Two lasers emit light of different frequency, so that part's true. And the light from the green laser has smaller amplitude, and that part is false. Okay, so because, right, it's brighter, green light has to be brighter, so it's a larger amplitude. I will tell you, this type of statement is one of the most difficult for students to catch, because you read the first part and then say, well, that's true, and then you have a hard time reading the second part because your brain automatically wants to accept the second part as being true as well. So this statement's not true either, because the second part of the statement's not true. It says two lasers emit light from different frequencies. That's true, and the light from the green laser has greater amplitude. So this is the correct statement. It matches, right, our idea of large amplitude and, right, larger, brighter light. And then it also falls in with the idea that the frequencies and wavelengths will be different for red and green. So light, like Roy G. Biv that we see here, this is Roy G. Biv. It's also what you see coming out of a prism, by the way. So that picture of Isaac Newton wowing the ladies in his laboratory with the colors of a prism. Yeah, so what they were seeing is this, of course, that was sketched in black and white, but is only part. So Roy G. Biv is only part of what we call the electromagnetic spectrum. And it turns out most of the electromagnetic spectrum is not visible to us. We can't see it. So we think of Roy G. Biv as being part of the visible spectrum. That's this part here that we're talking about, right? And the rest of it is invisible to us. Now, here's what I want you to know about this. I don't care if you necessarily know the wavelengths, okay, of light for anything other than, roughly speaking, we're seeing in red light 750 nanometers to violet to about 400. Typically, people see within around 400 to 750, and you can remember which end's violet because the shorter wavelength, right, will be the higher energy, and that's towards the right, and the red is lower energy, and it's towards the left. Okay. Now, but I do care that you know sort of what the different bands of electromagnetic radiation are called. So low energy, long wavelength is on this end. We have radio waves, and then we have microwave. Now radio, you can imagine, right? AM, FM, right? TV, cell phones, that all falls in the radio wave. And cell phones are almost in the microwave region. Microwaves, unfortunately, they're not like micrometers long. They're actually 10 to the minus 1 to 10 to the minus 3 actually meters. So this is like from a centimeter to a millimeter actually, right? That's what we call microwave. So your microwave, right, in your house uses microwaves to heat food up. And it turns out water absorbs microwave radiation really well, and that's by absorbing the microwave radiation, it heats up your food. Okay. Now, infrared is below red. That's what that literally means, right? And that's below red over here. And when we think about heat, have you seen thermal images of people's bodies, like where they're losing the most heat, or houses and windows where heat is being lost? That's all done using infrared radiation. Insects, many insects like mosquitoes can see infrared radiation. So when you're out at night and you get bit by a mosquito, it actually can see the carbon dioxide, which also absorbs infrared light, and your body heat. And so that's how it sort of zones in on you. One of the tricks that researchers use to capture mosquitoes without poisoning them is to take an ice chest, right? Like just one of those cheap styrofoam ones, cut a hole in it, and they throw dry ice on the inside. Now, dry ice is made out of solid carbon dioxide, and as it sublimes and goes into the gas state, CO2 comes out of here, and the mosquito, I don't know if I can draw a mosquito that well, little wings like this and a little pointy head and a proboscis for sucking your blood out. He sees that CO2 and will go to the source. Once he's inside the ice chest, it gets too cold for him to fly, and they trap him that way. Anyways, yeah, so bugs can see that. Insects can also see in the ultraviolet, so that is above violet. So violet's the highest that we can see, so ultraviolet is simply what's above what we can see. And this, both infrared and ultraviolet are broken down into different categories. Like ultraviolet, I think there's A, B, and C. Those are different bands in the ultraviolet itself, but all the ultraviolet is higher energy, and that's why it can cause skin cancer, because it damages the cells of your skin. X-rays get used for X-rays, right? They can penetrate through your body, and gamma rays actually can penetrate way through your body and all kinds of different things. They have much more penetration than X-rays do. These are the highest energies, and we see gamma ray bursts coming from space. We pretty much know that's some sort of star event that's creating that kind of energy. Okay, so radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. I'd like you to know the orders of those, but not necessarily the actual wavelengths. And then for visible light, I just want you to know it's between 750 and 400, roughly. Some people can actually see more colors than other people, so they can see further into the red and further into the violet than others. And more colors. There's actually people with more cones or whatever, different kinds of cones. They can actually see more colors within the spectrum.